Hello everyone. So, this is the first lecture of 6th week. So, we will be starting with quasi-Newton methods this week. Until now we have covered line search methods, the exact and backtracking line searches, and to find the descent directions we have discussed gradient descent method, and among conjugate gradient, the popular Fletcher-Reeves method as well as the eigenvalue eigenvector method. And in the last week we discussed Newton's methods and the variants the modified Newton method and the damped Newton method, right. So, we were able to rectify most of the issues that Newton's methods faced, except for one particular issue, which was the inversion of Hessian matrix, right. So, inversion of Hessian matrix is computationally very expensive, in the sense it takes a lot of time if n is large. Okay. So, it is not scalable. Okay. So, that is the reason we actually move to quasi Newton methods, okay. And that is what we will be learning this week. Okay. So, you can see that variants of Newton's methods are named along with Newton itself, right. So, we saw damped Newton method, modified Newton method, and now we have a few different quasi Newton methods. So, we will see the popular quasi Newton methods this week. Okay. So, fine, where do we start with? Please recall that for Newton's method, right. So, we had we considered the second order Taylor's approximation of f, right. So, Taylor's approximation second order is f of x is approximately equal to f of x k plus del f of x k transpose x minus x k plus half x minus x k transpose del 2 f of x k x minus x k, right. So, we might have written this as g k transpose and this as h k. I think that is fine. Okay. So, all right. So, from this, if you recall what we did in Newton's method, right. So, we differentiated this with respect to x and evaluated it at x star, which is the minimizer of f, right. So, differentiating the above equation and evaluating at x equal to x star, we get, so that is del f of x star, that is 0, which is g k transpose, this is 1 and this is h k into x star minus x k, right. And from here we actually got this direction to be d k equal to minus h k inverse g k, right. So, this was the basis of Newton's method. Now, how do we actually avoid the inverse in this step, right. So, if taking inverse is costly, if that is computationally expensive, so how do we avoid this step h k inverse, right. So, the idea is as follows. We consider that h k inverse and h k plus 1 inverse are close to each other, okay. They are not very different, because x k is x k plus 1 is x k plus alpha k d k, right. So, that means it is I mean the difference between xk plus 1 and xk is not too much. So, we expect the difference between hk inverse and hk plus 1 inverse not to be too much either, right. So, we try to update hk inverse to hk plus 1 inverse, okay. And I mean that is how quasi Newton method comes into practice, okay. So, how to avoid inversion of Hessian? So, idea is update hk inverse to hk plus 1 inverse, assuming that they are not very different. Okay. So, I am just giving the heuristics, this is not well defined statement, since I am saying very different and update. So, by update you can ask what does update mean, you can ask what does very different mean. I understand all that, I am just giving you a heuristic so as to understand what is actually happening in quasi Newton method, okay. So, that you are able to follow what is going on when I actually let you know the different methods and the algorithms that go ahead over there, okay. So, now let us define Bk as Hk inverse, okay. So, then we have, so I am just writing this second order approximation, the equation at the top again using this equation. So, we will have f of x to be f of x k plus g k transpose x minus x k plus half x minus x k transpose b k inverse x minus x k, right. So, it should have been h k, but instead I am writing b k inverse now, okay. So, yeah, if you take this definition in the idea above, I need to update b k plus 1 using b k, right. I need to update b k to b k plus 1, which means that I need to update b k plus 1 using b k, like how I update x k plus 1, x k plus 1 I am updating it as x k plus alpha k d k, right. So, in a similar way I need to update b k plus 1 using b k. How do we do it? Okay. I will differentiate this particular equation, whatever I have here, the last equation that I have written, and evaluate it at x is equal to x k plus 1, okay. So, differentiating the above equation and evaluating at x equal to x k plus 1, we get f of x k plus 1, sorry, actually del f of x k plus 1, which is actually g k plus 1, equal to, so this is I mean f of x k if you differentiate at 0, and here you have g k yeah, it will be g k, and here you have b k inverse x minus x k plus 1 minus x k. Okay. So, this is g k plus 1 minus g k equals b k inverse x k plus 1 minus x k, right, and define gamma k as g k plus 1 minus g k and delta k as x k plus 1 minus x k. So, we have delta k equal to b k gamma k, sorry, b k plus 1 gamma k, oh I am sorry, I should have written b k plus 1. So, this is Bk plus 1 gamma k. So, this is called as the quasi Newton condition. So, when you update Bk to Bk plus 1, you must make sure that this quasi Newton condition that I have written here is satisfied. Okay. So, yeah, that is basically I mean how we construct different quasi Newton methods. Okay. So, in this week we will actually see 3 different quasi Newton methods. Okay. One is called as the rank 1 correction, the other is the DFP method. DFP stands for Davidson, Fletcher and Powell, who found who discovered these methods. Okay. And the third one is BFGS method, which is Broyden, Fletcher, Goldfarb and Shano. Okay. So, these are the 4 optimizers who actually came up with these algorithms. Okay. So, we will see these 3 quasi Newton methods and the different conditions that you have or the differences in the algorithms that I mean these 3 algorithms, their performances and so on. Okay. So, we will start with rank 1 correction. Okay. So, let us say so yeah, I said we have to update Bk plus 1 from Bk, right. So, as the name suggests, we will update this matrix Bk plus 1 using a rank 1 matrix. Okay. So, any rank 1 matrix. So, note that Bk plus 1 is an n cross n matrix and Bk is also an n cross n matrix. Why? Because so yeah, we define Bk as Hk inverse, right. Hk is an n cross n matrix. So, the inverse is also an n cross n matrix, right. So, what I am going to do is update Bk to Bk plus 1 by adding a rank 1 matrix. So, of course, when you add 2 matrices, both have to be of n cross n, order n cross n, right. So, yeah, when you have beta so I mean when I say add a rank 1 matrix, it is of course an n cross n matrix, but the rank is 1. Okay. So, such a matrix can always be written in the form beta into u transpose, okay, where u is a vector, an n length vector, right. So, yeah, we will update it this way, but we need to find out what is beta and u, right. So, that I mean this equation is satisfied, right. Sorry, so that the quasi Newton condition is satisfied. So, yeah, we will figure out what beta and u are. Note that we want beta k plus 1 gamma k equal to delta k, which is what I have written here, right, the last line, delta k equal to Bk plus 1 gamma k, right. So, that means Bk gamma k plus beta u transpose gamma k equal to delta k. So, I have just substituted beta k plus 1 as beta Bk plus beta u transpose. Okay. So, note that this is a scalar, u transpose gamma k is a scalar, gamma k is a vector, u transpose is also a vector. So, the dot product is a scalar. Okay. So, I can write this as beta u transpose gamma k, beta is a scalar, u transpose gamma k is a scalar, into u equal to delta k minus Bk gamma k. Okay. So, since this is a scalar, I will fix, so let u equals del k minus Bk gamma k, right. So, in such a case, note that we need beta u transpose gamma k to be 1. So, therefore, we have beta equal to 1 by u transpose gamma k, and u is this. So, delta k minus b k gamma k transpose gamma k. Okay. So, therefore, we actually have b k plus 1 equals b k plus yeah. So, let us just u is what I have written here and beta is what I have written here. So, beta u transpose should be delta k minus b k gamma k delta k minus b k gamma k transpose by delta k minus b k gamma k transpose gamma k. Okay. So, this is what we call as the rank 1 correction update. So, whenever you update your B matrix using this particular equation what I have boxed now. Okay. So, that is the rank 1 correction method. Okay. So, I will write down the algorithm fully. Okay. So, yeah. So, we first start by initializing x 0 tolerance k equal to 0. Here we have to initialize b 0 as well. Okay. What is the because we are just updating here. So, there should be a starting point, and that starting point needs to be a symmetric positive definite matrix. Okay. So, it cannot be any arbitrary matrix. Okay. So, you need to initialize b naught, which is positive definite, please understand. Okay. So, that is another step that is extra when you compare it with the algorithms that we had discussed until now. Okay. All right. Now, while norm g k greater than the tolerance, so we first write d k is, so it should have been minus h k inverse d k, right, according to the Newton's method. But now we are considering h k inverse is like, I mean b k as h k inverse, right. So, it has to be minus b k g k, that is since h k inverse is b k. So, this d k should be minus b k g k. Okay. So, yeah, and you can choose alpha k by yeah, any line search algorithm. Now, so yeah, of course, it is I mean this is the next step we usually write, is not it, that is correct, but we cannot leave it here, because after this we still have to update b k plus 1, and b k plus 1 actually needs delta k and gamma k, right. So, let us update them as well. So, note that delta k is actually x k plus 1 minus x k, right. So, that is how we have defined it here, right. So, and gamma k is g k plus 1 minus minus g k. So, let us define them that way. Delta k is x k plus 1 minus x k, which is just alpha k d k, and gamma k is g k plus 1 minus g k. So, you can find that because you know x k and x k plus 1, right. So, yeah, use that to find gamma k, and here you should update b k plus 1 using the big equation that I have written on the top and have boxed it, right. Okay. And of course, k equal to k plus 1. Okay. So, you do this loop until norm g k is less than or equal to the tolerance, and finally output x star equal to x k. Okay. So, this is basically the rank 1 correction algorithm. Okay. And So, yeah, the first thing that we do after writing down an algorithm is to evaluate this particular algorithm for quadratic functions, is not it. So, let us do that, and I mean, so that is how we actually derived the theories for many methods earlier, is not it. So, you can recall that the conjugate gradient methods, either the eigenvector method or the Fletcher-Reeves, finds the answer in n steps for quadratic functions, and Newton's method finds it in one step if yeah, the answer exists, right. That is, if the Hessian of the quadratic function is positive definite, right. So, let us try the same with rank 1 correction as well. I claim that for quadratic functions this converges in n steps. Okay. So, let us write down this code for this particular algorithm and check whether yeah, the steps are followed or not. So, this is rank 1 correction for quadratic functions. Yeah. So, let me import NumPy. So, I would like to write a 5 cross 5 positive definite matrix like what we did for conjugate gradient and Newton's method. Okay. So, let H be random matrix which consists of integers between -9 and 9, okay, 5 cross 5 matrix. I want to make this positive definite. So, I am going to consider H into H transpose plus I, okay, and let me consider half X transpose H x plus B transpose X. So, B will be yeah. So, I can now define f of x as what I just told you, 0.5 into x dot h x plus b dot x, and grad of x is h x plus b. Okay. And now I have to do the initializations. So, one is x, I will again initialize it randomly to let you know that for any random x, I mean the answer is not, I mean the answer will be attained in 5 steps in this example. Okay. So, okay, so that was one thing to be initialized. The other one is k, and the other one is b, right, yeah, b 0, but since we are going to update b, I will just write it as b. I will write it as I itself, because we know that it is actually a positive definite matrix, right. So, all right, yeah, that is all I have to initialize. Now, while np dot lineal dot norm of grad of x greater than tolerance or 1 e minus x, since that is the tolerance we usually use. So, the first one is d equal to minus b k g k. So, minus b at grad of x, okay. And alpha, since this is a quadratic function, we will use exact line search, which is minus grad of x dot d by d dot h at d, okay. And I will now update x, x is x plus alpha into d, and I will also write delta. So, delta I will just write it as dl for brevity, otherwise I mean each of the time I have to write dl very big. So, I will just write it as dl, okay. That is just alpha into d, okay. And gamma is grad of x plus alpha into d minus grad of x. I could have written the same line, but nevertheless. So, finally, I need to update b, that is b plus delta minus b into gamma. So, I am writing something here. If you do not understand, please bear with me for a moment. I will explain what it is. By delta minus bk gamma, delta k minus bk gamma k transpose gamma, okay. So, I mean I have just written delta minus b gamma into delta minus b gamma transpose, okay. So, you might ask why is it so haphazard. So, I will explain it in a moment, okay. And k equal to k plus 1, okay. I should write print statements. So, percentage d and 1.3, 1.3. So, I have to write it 5 times. And for norm grad of x, that is one more. So, you have k, x of 0, x of 1, x of 2, x of 3 and x of 4 and np dot, okay. I will also print in the beginning. So, the other one I want, so this is all is the code. Since I want to verify whether I am getting the right answer, so I will find yeah. So, the answer you know that it is minus h inverse b. So, it is minus h inverse and b. So, let us print that too, okay. So, yeah, you do not need all of these. Oh, okay, there is an e missing, yeah. So, yes, and I need to modify, sorry, all of let us wait for a few seconds since it is connecting, yeah. So, yeah, you can see that we have got the answer in 5 steps, right, and you can verify that, yeah. So, y is the final line that you have is minus h inverse b, which is 0.1754, 0.2652, 0.8599, 0.4751 and 0.4581, which is what you got here. So, note that I chose a random h and a random b, random positive definite h and a random b. I also started with a random x, okay. My b0 was as simple as I, okay. But given that the function is quadratic, this method rank 1 correction actually found the answer in just n steps, okay. You can also, and note that I have not inverted h at all, okay. So, no inversion has happened here. So, this is just to verify whether the answer is correct or not, right. So, no inversion has happened, but I have managed to find the answer of any quadratic function in n steps, right. So, that is how good the rank 1 correction method is. So, in the next lecture we will understand more about rank 1 correction and then move to the other methods. Thank you.